talk about continuity today. Continuity. We're going to talk about a function being continuous. First, let me give you a very basic concept of continuity. At this x value, at x equal a, the graph is continuous if around a, that is for those say x values, I can graph or draw the curve without lifting my pen or my marker around a. And I did. And I did. Around a, I didn't have to lift my marker. Or maybe it's there and then it's up here. Well, around x equals b, I had to lift my pen. No matter how small of an interval you go around b, I have to lift the pen. I have this portion from the left and this portion from the right. I had to lift the pen. A function is continuous at an x value if you can draw it without lifting your pen. Okay, but that's not a mathematical definition. But it works. Now let's give a real definition. A function f of x is continuous at x equal a if the following, I guess, three conditions are met. If the following three conditions are satisfied. If the following three conditions are satisfied, then the function is continuous at a. The first one, I guess, comes in two pieces, 1a and 1b. The limit as x goes from a to the left exists. Stating what it equals is one way of showing that it exists. If this equals 7, then of course it exists. The second one is to show that the limit to the right of it, a little bit more than a, of f of x exists. The second criteria is to show that these last two limits are equal. Show that the limit, or verify that the limit as x goes to a plus of f of x is in fact equal to the limit as x goes from a to the left of f of x. So since both of these are real numbers and they're equal, why not say what it equals? Let's call it L for limit. They both equal the same value, L. And the last thing you have to show is that f of a, and this is really why I gave it a name in the last step, f of a equals that common limit. You must verify these three statements. You must verify these three statements. Okay, Now I'm going to state a theorem without proving it. No sense in proving it. Theorem or fact, polynomials are continuous everywhere. Continuous everywhere. Okay, for you to understand this definition, you have to understand what a polynomial is. So if you don't know what it is, look it up. Polynomials are continuous everywhere. So a problem might be is to find out where this function is discontinuous. Discontinuous means it's not continuous. Find out where this function is discontinuous. Okay. For g of x is equal to x squared 4, and it equals to 3x cubed minus 9 if x is greater than 4. Now, just the way it is, statement 3 will not be satisfied. Let me try to write down those 3 criteria. The limit as x goes to a of f of x, and the limit as a goes to the right of f of x must both exist. Must exist. And b, 1b, they're equal. The 2 and 1a are both equal. These two, this and this, they must be equal. And 1c is, f of a must equal the common answer in 1b. This is shorthand notation. Now, what's going to happen is, let us just suppose that 1a and 1b are we verified it. F of a is not, so we'll come back to this in a moment. Now, this is a polynomial, and this is a polynomial. That is, when it's less than 4, this is continuous. Maybe it looks like that, and here's 4. And after 4, you have a few cases. Case 1 is they don't link up, that is, you have to lift your pen or marker, and in case 2, they do link up right here. Okay. But nonetheless, at 4 is not even defined. Which rule would you use when x is 4? The top rule or the bottom rule? You only use this rule when x is less than 4. Well, since 4 is not less than 4, we won't use the top rule. And you only use this rule when x is bigger than 4. Like if somebody asks you what g of 5 is, what is g of 5? Since this x value is more than 4, you use 3x cubed minus 1. If I ask you for g of 0.5, that is g of a half, since x is a half. Since a half is not bigger than 4, but a half is less than 4, I'll use the top rule. But 4, x equals 4, doesn't satisfy either of the rules. It's not even defined at 4. So f of a isn't even a value. It's not defined. So how can it equal L? How can it equal a common limit? Okay, so I wanted to state that. So immediately you can say it's not continuous at 4. Immediately, boom, is discontinuous at 4. In fact, it's not going to be discontinuous anywhere else. But what I am going to do is, I'm going to say it can equal 4. Okay, I just put an equal sign right there. So basically, the only place it may be discontinuous would be at 4. Because we don't know if it links up well. Again, here's x equals 4. To the left, you have this nice quadratic function. It doesn't equal x is 4. And it's not defined for more than 4, only for x is less than 4. The next function, 3x cubed minus 9, very nice cubic function. It's defined from 4 and above. Well, it may be here and go that way, or it may be up here and go that way, or it might go this way, or it might, all those cases that I drew so far would be discontinuous. Or it might actually fill in this open hole. It might fill it in. And then it would be continuous. That's the only case when this function would be continuous. Yeah. So we need to basically, well, let's erase all of this. We need to verify the three statements below. That's the Bible in these problems. You have to know how to verify these few statements. So we need to look at the limit from the left and from the right. That's what 1a talks about. What is the limit as x goes from 4, as x goes to 4 from the left of f of x? And what is the limit as x goes from 4 to the right of f of x? Well, let us figure out what f of x is. What is the definition of f of x? Well, if x is a little bit less than 4, or a lot less than 4, if x is less than 4, we use the quadratic. We use x squared plus 3x minus 5. And we plug 4 in. We get 4 squared plus 3 times 4 minus 5. We get 16 plus 12 minus 5. We get 23. We get 23. So the left-hand limit, 23. Let's look at the right-hand limit. Well, when x is a little bit more than 4, let me write limit first. When x is a little bit more than 4, we use the rule that talks about x is more than 4, namely 3x cubed minus 9. So we need to see what 3 times 4 cubed minus 9 is. We need to see what this minus that is. Well, I know what that is. It's 9. Here, it's 3 times 4 cubed. 3 is 3, and 4 cubed is 64. I think you should realize you're going to get way more than 23. This looks like 192 minus 9. This is what? 183. They're not equal. It doesn't equal to 23. 1a has not been satisfied, so you say G is discontinuous at x equals 4. G is discontinuous at x equals 4. Okay, actually, let me go back for a moment. Okay. What I said is not true at all. I said 1a has, I don't know why I didn't call this 2 and 3 like I did earlier. 1a and 1b were satisfied. They do both exist. I found both limits. The left limit was 23, and the right-hand limit was 183. Sorry, I did find it. But condition 2 is not met. It says the two limits must both be equal. The two limits in 1 must be equal. They weren't. 23 doesn't equal 183. Okay, so we don't even have to verify or check statement 3. How about this one? H of x is equal to the following. It equals to 3x plus 5 if x is less than 4. It equals to x squared plus 1 if x is in between 4 and 7, and it equals to, I would pick 7, it equals to x cubed, okay, it equals to x cubed, here, need 43. I want to end up with 50. So what? I take away 293. Take away 293. And this is if x is bigger than 7. And one of these should not say equal. Say the bottom. So suppose we have this, and if you didn't understand how I got the minus 293, don't worry about it. You don't have to make up the problem. Now, the first curve is a polynomial. It's a line. Lines are always continuous. You don't ever have to lift your pen when you draw a line. Just don't go beyond 4. X squared plus 1 is a quadratic. That's a polynomial. It's always continuous. If it looked like this, we're only going to keep the portion between 4 and 7. We are only concerned with this portion. And it can actually equal 4, because it does say equal, and it can equal at 7, so it gets filled in. But nonetheless, it's continuous. If you take a portion of a continuous function, that portion will be continuous. Polynomials are continuous. The question is, do they link up well? Well, where do they link up? The first function stops at 4. The second, or the first part ends at 4. The second one picks up at 4. Is it continuous at 4? The second function stops at 7. Oh my, the third function picks up at 7. Is it continuous or discontinuous at 7? So 4 and 7 are the points that we're worrying about. In the safe space, I'll ask the question here. Is h of x, excuse me, to the left there is. Where is h of x discontinuous? Now the answer may be nowhere. The answer may be it's continuous everywhere. So the cutoffs are at 4 and 7. So let's look at 4. What's going on at 4? Well, 1a is the limit as x goes from 4 to the left of f of x. 4 with a minus sign, that means less than 4. If you're less than 4, you use 3x plus 5. Okay, you use 3x plus 5. Plus 4 for x. So you get 3 times 4 is 12, plus 5. 12 plus 5 is 17. Okay, so 1a has been satisfied. The left limit exists. But more importantly, we even have the answer. 1b. What is the limit as x goes from 4 to the right? That means a little bit more than 4. Well, x is allowed to be more than 4. Can be a lot more than 4. It has to be less than 7. But it can be a little bit more than 4. So we use x squared plus 1. And wherever you see x, plug in 4. So 4 squared plus 1 is 16 plus 1, which is 17. Now statement 2 has been satisfied because the two limits are equal. Now, statement number 3 says that f of 4 must equal the common limit. Okay, f of 4 must equal the common limit. Well, I kind of drew on the graph, or on the definition, but remember we had the equal sign right here. We had an equal sign right there. So x can equal 4 or 4 can equal x. So we use x squared plus 1 to find f for 4. 4 squared plus 1, 16 plus 1. Does this equal the 17? Does it equal the common limit? And of course it does. 17 equals 17. I've been making one, okay, just a minor error. The name of the function is h. The name of the function is h. Actually, more than once. I've been saying, what's f of x? I've been meaning to say here and here, what's h of x? The name of the function is h. So I should just have an h here. What's h of 4? Okay, so it's continuous at 4. But they're asking us, where is it discontinuous? So we're done with that. Now let us check our other questionable position. 7. Maybe it's discontinuous at 7, maybe not. But we have to try. Okay, so for 7, what's 1a? What's the limit as x goes to 7 from the left? What's the limit as x goes from 7 from the right? That would be 1b. I'm going to say h of x this time, I hope. H of x, when x is a little bit less than 7, x is less than 7, h is x squared plus 1. X squared plus 1. So you get 7 squared plus 1, which is 49 plus 1, which is 50. Now, the limit where x is a little bit more than 7, well, more than 7, if 7 is less than x, that means x is more than 7. This is the rule we use. The x cubed minus 293. So I get 7 cubed minus 293. If I'm not mistaken, that's 343. And I ask myself, what do I take away to get 50? And I claim it's 293. So I do get 50. And statement 2 has been satisfied. Okay, 1a and 1b are satisfied because both limits, well, some seemed wrong there. This should be 293, excuse me. Just like it says, the typo. Okay, 1a and 1b are satisfied. Why? Because I got limits. The left limit exists and the right limit exists. And statement 2 has been satisfied because they're both equal. Now statement 3 says that h of 7 must equal the common limit. It must equal 50. And either if it equals 50, it's continuous. If it doesn't equal 50, it's discontinuous. Well, when x is 7, it says right here, x can equal 7. X can equal 7. So I use x squared plus 1. X is 7. 7 squared plus 1, which is 49 plus 1. You know what? It equals the right-hand side. It equals 50. So, what's the final answer? H of x is continuous everywhere. Or if you want to be really precise, they ask where is it not continuous. You can say x is discontinuous nowhere. It's continuous everywhere. It's continuous the way it is. Some functions are continuous everywhere, some are not. Now let's look at some cases where there are discontinuity points. Let's look at a case where number 3 is not satisfied. Suppose I tell you f of x is equal to x squared plus 1 if x is less than 5, and it equals to 5x plus 1 if x is bigger than 5, and it equals to, I don't know, 2x plus 4 if x is identically 5. Well, again, each of these are these being this, this, than this. They're all three polynomials. So on its region, it is continuous. For example, let us actually draw this graph. X squared plus 1 goes up 1. It's the quadratic. Looks just like that. But we're not supposed to go past 5. We're not supposed to go past here. Since it doesn't say equal, I put an open circle there. And this portion of the graph, history, it gets erased. It gets erased. Now the next graph, 5x plus 1, 5x plus 1, well, if x is 0, remember, another name for f of x is y. If x is 0, 5 times 0 is 0, plus 1 is 1. If x is 5, and by the way, when x is 5 here, that y value is going to be 26. That's where 26 is going to be. Think about y. Now, when x is 1, I meant to say, okay, if x is 5, I mean to say. If x is 5, then y is going to be 5 times x, that is 5 times 5, or 25, plus 1 is 26. So I have 2 points. When x is 0, I go up 1, which happens to be right here. And when x is 5, I go up to 26, which happens to be right here. And I get this line. I get that line. But I only keep the portion of the line that's bigger than 5. That is, I keep this portion. Notice nothing has filled in that circle yet. And this is erased. It's not part of the graph. Why is nothing filled in when x is 5? Because we haven't talked about when x is equal to 5 yet. Now when x is 5, y equals 2 times 5, which is 10, plus 4, 14. That point, believe it or not, goes right there. This graph is not continuous at 5. It's not continuous at 5. Well, the thing is how can you prove it? Now before I prove it, I do want to comment the only possible point was at 5. Because the first graph is being a polynomial, x squared plus 1, is continuous less than 5. This graph, being a polynomial, is continuous more than 5. And to be honest, 2x plus 4 is 14. Because it's only defined when x is 5. Don't use 2x plus 5 unless x is 5. It says it. Y equals 2x plus 4 if x equals 5. Okay. So it's only, it might be discontinuous at 5. And we claim it is by the graph, but we need to prove it. What is the limit as x goes to 5 minus of f of x? Well, if you're little less than 5, you use the x squared plus 1 rule, because it says x is less than 5. And when you plug in 5, x squared plus 1, when you plug in 5, you get 5 squared plus 1, which is 25, plus 1, which is 26. So 1a is satisfied. That is, the limit exists. We can even tell you what it is. We didn't need to verify, to say that it exists. But finding out what it is, that's one way of saying it exists. The limit as x goes from 5 above. Well, if you're more than 5, you use 5x plus 1. And when you substitute this number in for x, you get 5 times 5 plus 1, 25 plus 1, which is 26. So 1b has been verified. So two limits, well, the right-hand limit exists. So 1, all of 1 is verified. Both limits exist. Now, number 2 has been verified because the two limits are equal to one another. The left limit and the right limit equal. Now, number 3 is, I'm looking at the name of the function this time, is f for 5 equal to the common limit, which was 26? Well, f for 5 is 14. 14 does not equal 26. So, we say for our final answer, f of x is discontinuous at x equals 5. So that's a case where number 3 cannot be satisfied. For 1, when I say 1, I mean 1a and 1b. 1 was verified and 2 was verified. That is, they both passed. 3 failed. So it was discontinuous. Now let's look at a function where number 2 fails. Okay, let's see how it might be that condition number 2 fails. So suppose we have that j of x is equal to 3x plus 1 if x is less than 10, and it equals to 2x plus 5 if x is greater than or equal to 10. Now number 2 is going to fail. 1a. What is the limit as x goes to, so the only place it might be discontinuous is at 10. Why? Because these are both polynomials, they're both lines. How can you draw 2 lines and it be discontinuous? Well, if one line goes like this and the other line goes like that, there's a jump. You have to lift your marker. Here, I'm drawing it, and right now I just had to lift my marker. Okay? Now, of course, when I say draw 2 lines, I'm not allowing you to draw a line, I don't know, like this, and then like that. Why? Because the first line went from, I don't know, 2 to 6, and 2 to 6, the x value, and the second line, it went from 3 to 10. In other words, they're not functions. Why are they not functions? Because they fail the vertical line test pretty badly between 3 and 6. But other than that, it's discontinuous if you have to lift your pin. Okay, so what is this left-hand limit at 10? Well, when x is less than 10, because that's what this symbol means, you're less than 10. Let's even make it negative 10. All of these 10s are negative 10. You're a little, so let me write it more neatly, because this tends to bother people. The limit as x approaches the number negative 10, but a little bit less, like negative 10.001. So which function do I use? I use the one that says you're less than negative 10. 3x plus 1. So you get 3 times negative 10, which is negative 30, plus 1, which is negative 29. You owe somebody $30, and you actually give them $1, you don't owe them $31. And if you do, stop paying them, because you'll never pay them off. If you pay them and you keep owing them more, something's wrong. I wouldn't pay somebody if I kept owing them more. We're not talking about interest. Okay, so 1A has been verified. Okay, 1B, the limit as x goes to -10, but a little bit more. If you're more than, there's the more than symbol. If you're more than -10, you use this rule. 2x plus 5. So you get 2 times -10, which is -20, plus 5. You take out $20 from the bank, and then you put back 5, you took out 15. Since these numbers are not equal, number 2 has not been verified. Number 2 failed. You can immediately say, is this continuous at x equals -10? Now, just for the record, every time 2 fails, 3 has to fail. Why? Because j of -10 must equal the common limit. But we don't have a common limit. These numbers were not equal. So every time 2 fails, you have to have 3 failing. Because how can j of 10 equal dne? Does not exist. The common limit does not exist. Okay. And just for the record, if j of -10 doesn't exist, you can't say, oh, they're equal. Does not exist equal does not exist. Nonsense. They're not equal. So every time 2 fails, 3 must fail. Okay, so I just gave an example now where 2 failed. And I think the last one was where 3 failed. Let me look that up, please. Okay, so the last one was where number 3 failed only. This was an example where 2 failed, which means don't even bother to verify 3. It failed. And now I'll give you an example where 1 fails. Let me give you an example of where 1 fails. Suppose I tell you, I don't know, f of x is equal to 1 over x if x is less than or equal to 0, and it equals to 2 plus x if x is more than 0. Well, let's look at the limits. The limit as x approaches 0 from below, from the left, that is less than 0. X is less than 0. I use 1 over x. This is 1a. And for 1b, the limit as x goes from 0 to the right, if x is more than 0, I use this rule. Well, for the record, 1b works. 2 plus 0 is 2. It exists. But here, you get 1 over 0, which is undefined. That is. So let me write that. That is. The limit as x goes from 0 below of f of x doesn't exist. It doesn't exist. So here we have 1 failing. You didn't even have to do 1b because 1a failed. Now, this 2 has to fail. And then, now, what would it mean for 2 to fail or not fail? What it would mean is, to fail is if the 2 answers were not equal. Well, if you don't know the first answer, then they're not going to be equal. And then number 3 is going to fail because f of 0 cannot possibly equal the common limit, because the common limit doesn't exist. Okay, so if 1 fails, 2 fails, and 3 fails. So I guess it has a domino effect. If 1 failed, and so did 2 and 3. If 1 passed, but 2 failed, 3 failed. Once he failed, the next one fails. And if 1 passed and 2 passed, you can have just 3 failing. But you don't have to even know that. Once it fails, you're done. Move on. It's discontinuous. So, to answer this last question, let me go back, please. I guess the question is, where is f of x equal to this discontinuous? And the answer is f of x is discontinuous at x equals 0. 0 is the only cutoff. Both 0 is the only cutoff. 1 over x, that's not true. 1 over x goes this way. It's always continuous if you're less than 0. So I did have a slight problem. I shouldn't have had it equaling 0, but on the bottom one I will. 2 plus x can equal 0. 2 plus x looks something like that. Okay, and it can actually equal here. The function is discontinuous at 0. Now what we're going to do is we're going to do these similar problems all over again, except that is we're going to determine if our function is continuous or discontinuous, or where is it discontinuous, using graphs. I'm going to give you a graph and say, is it continuous? Where is it continuous? Where is it not continuous? So, I draw you a number of graphs, and you're to decide whether or not it's discontinuous or not. Two more. All right. 1, 2, 3, 6, 5, 4. Okay. Number 1, and all these graphs really should be labeled with the x and y axes. Just trying to save a little time. The first graph, number 1, is continuous for one reason. I can draw it without lifting the marker. Done. It's continuous. Number 2 is discontinuous because I have to lift my pen right here to fill in that point and then to come back. So this is continuous everywhere. This one, let's call this 3. This is discontinuous at x equals 3. Let's call this -7 and this 9. This function is continuous everywhere, so I don't have to lift my pen. The circle at the beginning is okay. So continuous everywhere, CE. But you can't read that, so we'll put it here, CE. The next graph, I can graph without lifting my pen. I mean, in reality, I can't graph because I have to stall way up at the left, and I never really finish. But other than that, it's continuous everywhere. This graph, I have to lift my pen right here to continue. If this is 11, it's discontinuous at x equals 11. X, y, 2.5. I have to lift my pen right here and pick up there. This is discontinuous at x equals 2.5. And that completes the lecture on continuity.